as well. Okay. So any new lesson you have learned at school?
We learned vector cross products.
Cross product. Oh, very fast. So have you started projection before that? Do you know what is projection?
Yes, but not in 3D vectors.
That is 3D vector. Interesting. I saw your curriculum. Doesn't matter. You can show me your textbook. I will ask a question because normally we start the projection first, because that can be very useful to understand the vector in 3D. Okay, right-hand row, product row, 2.6. You jump. Did you study 2.5, 2.4?
No, we skipped 2.5.
Oh, it's 0.5. You skipped 5. Ooh.
Yeah, we'll come back to it.
You come back to, oh yeah, wow. Okay, product, vector product. So we have encountered vector product. Now, do you know how to solve this problem now? Can you enlarge your screen, enlarge your book a little bit? I only see part of the getting. Yeah, I can see a large black frame. Oh, can we just enlarge your central part slightly? 100%?
I don't think I can.
Oh, that is maximum, right? It's probably something to do with your resolution, but I don't want to go that far. So you are using full screen now, right? Are you using full screen? Oh, yes, probably that we can't do much because our screen have different resolution. Anyway, I'm trying to read if you can zoom in. So which particular part you want to try? So this, you can enlarge it. So you know what is the right-hand rule now, right? So then can we try to work out, these are definite cross product. See the cross product is just 2 examples. So here we have used the notation of the n hat. Did you call it n hat? Hat.
Yeah.
Hat means unit, is unit vector, which just like IJK, which gives a specific direction in 3D space. In this case, they just denote this direction, the new direction of the product as n, right? That's it. So basically, there are 2 ways to denote this cross product. Can I participate? I can't.
I don't think you can do it when I'm sharing the screen.
Yeah. That's strange. Anyway, any question perhaps we can discuss directly?
I think I just want to go over cross products.
Cross product, yes.
Yeah, just like a basic and thing.
If I
doesn't have to be based off.
If I count right, I just look at this. This is just IJK. Okay, yes, we can go to whiteboard. I can show you what is the basic idea about cross product. Yeah, it's called the vector product. It's also called the vector product because that allows you to work out. So basically, when we started the vector, right? That is some background, I think. And the vector just like scalars. Okay, so vector. We're starting the numbers, scalars. Can we just tune it together? So basically, we're starting from scalar, right? We know scalar, just numbers, and then now we are starting vectors, right? And later on, we will study metrics, right? In that I noticed in your curriculum, right? So these are just mathematical quantities. The difference between that is that in the scalar, we can only denote the scalar by, for example, we just use x, right? We can use x denote the one value at a time or one variable at a time. Okay. So in terms of variables, so how many variables we can describe. For the scalar, we have 1. Okay, it's just 1. But for the scalars, for the vectors, we can increase the number to 2, right? And by the time you start a matrix, we can go more. So basically, what is different is when you start vectors, we can have use, for example, A. I prefer use this bold notation for A. And that give you two pieces of information. So basically, they get 2 components. So that is AX and AY. Okay. Can you see that is how we can use the 2, we can describe 2 variables when we use vectors. Okay. So whenever we discuss this new quantity, mathematical quantities, we were asking how to do the 4 rules. Okay. You will notice this is just the basic question people were asked. When we deal in the scalars, we ask you the various algebra rule. For example, we have, you see, you have the A plus A plus B equal to B plus A, right? And also A multiplied B equal to B multiplied A, and so on. So that is part of the 4 rule. 4 rule means just plus, minus, multiply, and divide, right? So in I think you have done the first. We have done that before. So that is we starting from we studied a sum and the difference, right? And now you are starting. Well, I just give you the location, and now we are dealing with product. Okay. So we know how to deal with how to use the product of the scalars. But we are learning how to use product of vector. Okay. So the cross product is one of them. Okay, I prefer to follow the logic of your textbook. So there are 2 types of the product. One is called, talking about the product, and one is called the scalar product, or we call the dot product. So we can things that we can compare. You see, we have a scalar product. And then we have, today we're going to study the vector product. So you can see that is different from the scalar, isn't it? When we're dealing with scalar, we know the product, okay? How can you divide this product into 2 types? Well, that is because we're dealing with different quantity. So this is a mathematical quantity, mass quantity. Of course, for the dot product, we know for the scalar product, for the dot product, they also call the dot product. Did you teach it to you?
Yeah.
It's called the cross product, just the name. And dot product is because the name is used because of the form. For example, A dot product B, right? So in this case, in this particular product, what we get is just the scalar, you see, and also we have to consider the angles between the 2 vectors. Okay. Now, by way of contrast, we can now introduce a cross product. See, they are all product, but they have different names. See, this is how the name is called. Dot is called the cross. So if you how can we define the cross product? And we have studied this cross product in physics, right? And so that's one application we can apply the vectors in physics. We know that the dot product will give you a new vector, can we call it C, right? That is different. So when we're dealing with scalars, the 2 products after cross product, what can you guess? So this is just amplitude, right? You get a scalar. Is that strange? Both A and B are vectors. However, the dot product will generate the scalars. Okay.
Yeah.
So that is difference between these 2, the product of 2 vectors. And in addition, we know that, and that's why I use this notation. If you just consider the amplitude of the 2 product, right? then that cross product can be simply written as A multiply B multiply sine theta. Can you see? This also is different. This is sine theta. This is not cosine theta. Okay. So I'm talking about the magnitude. Did the teacher show you that if you just oh, by the way, another thing you need to know at this stage is that the cross product obey the right-hand rule. So the right-hand rule tells us that if you have two vectors, if you do have the A with different color, A, B, and the product, can we use the red color is C. Where is the C? Is C. You see that? So these tell us that the cross product, oh, what happened? It's jumping to the, okay, just, all right. So let's just make sure, can we draw the graph? Can we draw the plane? It's had to draw the plane. Oh, they cannot do 3D plane. Okay, they can draw it. I can draw it then. So basically, you can see that here we would get the plane. You see, you can imagine in the 3D, this would be the plane. The two vectors will be on the plane. So if you just extend that diagram, so we should be able to get something like that. Can you see? We should get the plane. Can you imagine there is a plane? There's a 3D drawing. So the first two vectors, both A and B, are on the same plane. So this is something we need to understand, right? So that is why in your textbook they use n. They use n hat. They use n hat. So they denote the C in your textbook. If you refer to your textbook, they denote. So this, can we just write down here? This is A, and this is a B, the second vector. And this is C, you see, this is C. And they denote the C in this diagram as C multiplied n hat. N hat is just the directional vector of this plane. And eventually we are going to start how to describe the plane in the 3D. So this N, can we just draw that somewhere? It is parallel. This is just use this color, can you see? This is called the directional plane of this plane. So when we define the direction of plane, we have to use a vector and whose width. So whenever you see this, or if you have seen this absolute notation, you know that it actually represents the magnitude. Okay. So this notation in vector is called the magnitude. Magnitude. So similarly, this is magnitude. Can you see that? It also represents the magnitude, not direction. By the way, you can also argue these two variables come from the both the direction as well as the length. Okay. So that is how we introduce the right-hand rule to determine the direction of the product, direction of vector product. Does that make sense now?
Yeah.
In particular, I noticed that in on the other side of your textbook, we are discussing this the basic direction 3D directional vector. So we can, if I draw that first, so we got X, we got XY, and we got the Z. That is how to use the Cartesian coordinate in the 3D space. And according to right-hand rule, if this is X, this must be Y, can you see? Can you tell me which would be the direction of Z by right-hand rule? Right-hand rule. Yes, that's right. So that is because when this is a convention that we used to determine the relative orientation of the three axes in the 3D space. And in addition, we can also introduce what we call the unity vector, unity directional vector in this case. For example, if we just choose the unit length for the amplitude, so this is X, this is Y, so this is 1, 2, 1, 2, 1, 2. Then we can introduce a 3 vector, which were used as a directional vector. One is X, you see.
Mm-hmm.
Another is what? This is J. So that is the third one. I use a consistent result notation that this red one will be the product, vector product.
Mm-hmm.
So basically, by introduce IJK, I use I, is a J. Look at the 3 vector now. This is K. Then we can determine the direction of the 3D vectors. See? So this is a 3D vector. Sorry, this is not a number. This is a variable. This is a dimension. This should be. This is a 3D vector, not necessarily 2. Actually, this I'm wrong here. When we talk about the vectors, we're talking about the how to say, the rank. So this is not accurate. Okay, this should be called. It's called the rank. They call it rank, not a variable. Rank. Okay, so this is just rank, just like how many dimension. For the matrix, that would be 3. Okay, not these 2, but this is just 2D vector. How can I describe it to you? So basically, when we started the vector, can we just draw an arbitrary vector? Can you see? You see this color, just with white color. If I draw the so we can define the vector. Can you see? Do you remember this is a positional vector? Do you agree?
Mm-hmm.
The position vector is used to determine the position of any point in this 3D space, right? For example, if this is the case, then this position vector can be used as R, right? Mm-hmm. This is a vector in a 3D space. So how do you remember, how do we determine the position of this position vector? How do we determine the position of position called P? By using this directional vector.
Mm-hmm. So like I plus J plus K?
No, we need to use this R. Can you see this R is a vector? Mm-hmm. That can be written as 3 components. In this case, we know the coordinate is X, Y, Z, right?
Mm-hmm.
So therefore, for the position, these 3 coordinate is actually the components of this position vector, X, Y, Z. Alternatively, we can use the component. This is matrix form. You see, this is a matrix form of vector. So this is a matrix form. The matrix form. Alternatively, we can use components form. Here we can introduce this notation: xi, yj, and plus ck. So this still represents the vector, but this is called the component form. Component form. So a position vector can be represented by either a matrix form or component form. Does that make sense? Yeah.
Yeah.
So that is the basis we used to describe the position and the straight line as well as a plane. So eventually you will introduce the notation, how to define, for example, eventually you're going to learn how to describe or represent, represent a point, a position, right? A point, a line, a straight line, okay, and a plane, a 2D plane, right? In 3D, so in 3D space. So that is what we're going to learn in the future. Of course, before that, we have to get familiar with how to define the point in the first place, because after all, in terms of geometry, the point is a basis, right? The point is a basis. And by the way, how can you imagine how to define the straight line without much reading of your textbook? Oh, by the way, how to define the point line? So that is something we need to understand. For example, let's just study. So, for example, when we study a point in how do we define a point in 3D space? Do you want to try? Just use the idea we just introduced, using vector. Probably that will help you to understand what we just discussed today. How do we describe this 3 point? You use a vector or not? You use so what is this? This is a sum of 3 vectors, right? Can we translate your idea? So this is the sum of 3 unit vector, right? Unit vector. Is that what you mean?
Yeah.
What do you think? Is this vector as well? The sum of vector. So we jump now. The vector plus vector, what do we get? This is just basic idea. If you got 2 vectors, do we get the vector as a or scalar? Sum.
Oh no, it would be a vector.
It would be the vector. So that v, can we use your notation? That v will represent the sum of 3 vectors, right? Does that represent the point? Can we use a graph to illustrate your idea? So you have this is 3D diagram. Okay, can you illustrate your idea and to find the sum of these 3 unit vector? So that is a z. This is a y. This is x. Okay. Oh yes. Where is the sum? So this is I. Can you see? I just follow you. Oh yes, that's right. You're right. Yeah, you're right. Oh, that's a good idea. So basically, that is the sum of the 3 vector. 1, right? And 2 is this one, is y direction. Oh, sorry. It's y. Can do it probably is a y direction, right? And then go to another unit vector with the same. So in this case, you are just using 3 unit vector. All right. So that gives you vector. So for sure. So they give you the vector, but that only tells if that is a, can we call it P? So what is the coordinate? Can you tell? What is X and Y in this case? This is origin. This is unit 1. And that will represent y equal to 1. And presumably that will represent, it will represent z equal to 1. Okay. Can you write the, oh yes, 1, 1, 1. Okay. All right. So therefore, your position can we call the P1, that only represent a particular point. If you write this point, do you agree? This vector. So V is the sum of 2 vectors in this case, all right? But from what you write down here, this, can we just say this is a one probability, okay? Okay. Now, how about it is described another position, can you see? How about Q? Can you go to the Q? And this whose coordinate is that coordinate is if I use the -2, right? and -3 and the +4. Now, how do we write the position of P in terms of vector? So we just continue our exercise. Yes, you are right. But that special vector owner can describe very just one. Okay. 2. Yes, that's correct. Right. This is sum, right? Can we introduce the vector to represent? Can you see? Can we call this RQ or RQ? Can we? It's still vector, isn't it? So that would be R. Can you just rewrite it as RP? Can you see that? So that is how to define that is how to represent a point in 3D by using the sum of 3 vectors. Okay.
Yeah.
So in general case, how do we describe the position? Say the R position, whose coordinate is X, Y, Z. How can we describe this R arbitrary position by use a vector? Do you want to try? Using the same approach. That's right. Yes, you're right. You're right. So basically, and that can be alternatively written as we just mentioned. Can you see X, Y, Z? That's clear. So that is step 1. Okay, I will follow your curriculum. So we can now confidently describe any position in a space. All right. Give you just some extension. If we apply this idea to physics, can we find the velocity? How do we find another this example 1? We extended this idea, go to example 2. How to define the velocity to denote the velocity of a particle, a moving particle. In 3D space. Do you want to try?
Wouldn't it be the sum of the vectors?
No, I think we discussed this last week, right? Do you remember? We're talking about application of vector. So this is a little bit of extension. So you have to think how do we define the velocity in physics? How do we define the velocity, which is a vector, right?
Would it be using unit vectors? So
no, you have to use the physics knowledge now. What is the relation between the position? Oh, by the way, before that, can we discuss this one? Probably this. Can we just go to the second example? Is instead how to determine. This is just to determine or to describe. Can we say just to represent the displacement? Do you remember we used the displacement idea when we started the motion? How do we define the displacement? Yes. Do you remember when we started 1D motion, right? When we started 1D motion, for example, an object is just merely moved along the x-axis, either forward or backward. So the position of x at the time t can be written as xt, all right?
Mm-hmm.
And that is a displacement of, after a while, the object will move to that position, can you see? So the position vector change, that would be the xt plus delta t, right?
Yeah.
So how do you remember how to define the displacement? So in this case, the displacement in the 1D, so this is a 1D motion. The displacement, do you remember how to denote the displacement? Sometimes we use S, but sometimes we just use a delta x, can you see?
Mm-hmm.
Delta x just the change in position. Okay, how do we define the change in position?
Xt plus delta t minus t.
Yeah, that is xt plus delta t, right?
Mm-hmm.
Take the x at time t, right? Okay, do you remember how do we introduce the velocity? Do you remember when we first discussed the average velocity, right?
Mm-hmm.
That will be simply equal to delta x over delta t, right?
Yeah.
And also, after we have started calculus, we know that velocity can be defined as a limit. Do you use this notation in your physics or not? Not yet.
Not yet, but
yeah. In mathematics, we know, right?
Mm-hmm.
By definition, what is this limit? It's called instantaneous. It's called instantaneous velocity, right?
Mm-hmm.
Instantaneous velocity, accurate velocity. Is dx dt. Do you remember?
Yeah.
So the first derivative.
Mm-hmm.
Okay. So if we extend this idea to a 3D, for example, let's just draw this. For example, this is a trajectory. So the object, like the satellite or the a flying object, in space. For example, the traveling in space in this trajectory. Okay. So mm-hmm. at a different position, for example, from P, so this is a P to Q, right? So that will travel at a certain displacement. What we can do? We can use the position vector we just known. For example, this is our origin. Can you see? That would be the position at T.
Mm-hmm.
And another vector can use a slightly different color, the purple one. That'd be this one, Q. Can you see?
Yeah.
So instead of use just X and Y, here we can simply use the two vectors, right? So that is, can we say this is R vector at time T. This mm-hmm. is R vector at T plus delta T, right?
Yeah.
Okay. Can you represent the displacement in 3D? So this is a 3D in a 3D space. So this is origin. You see, this is origin. You want to try? By definition, so the displacement, I just need to know, the displacement is just denote the delta R as a difference between the R
mm-hmm.
at T plus delta T, take R vector at T. So that is a mathematical representation of the displacement.
Yeah.
Graphically, can you describe this? Oh, by the way, do you think the displacement is a vector or scalar? Difference?
Scalar.
Oh, interesting. We just discussed this sum.
Oh, wait, no.
Yeah, how about difference? Vector. Yeah.
Because it has magnitude as well.
Yeah. It's still vector, isn't it?
Mm-hmm.
So it is clear that displacement is still a vector, right?
Mm-hmm.
Can you use the vector to describe the displacement in this diagram? I think your teacher didn't ask this question.
No.
Yes, that's right. That's right. That is how to describe. After all, you can forget about the physical definition. You can simply, you see, that is why when you start Math C, sometimes they will apply mathematics, right?
Mm-hmm.
Do you think which field is often choose to apply mathematics?
Physics.
That's right, not chemistry, not biology. Okay, so that is why. So you can, in this case, you can always ignore their physical meaning. You just consider, we are asking to denote the difference between two vectors. Does that make sense? Yeah. Okay, now let's just return to physics. What is the direction of velocity in these two cases? If that is this trajectory. Direction of velocity?
Like southeast?
No, must be tangent, right? The tangent direction, okay? Must be the tangent direction. So that's one. Can you see?
Yeah.
So in this way, so that is a velocity. These two vector also represent. We're talking about that definition afterward. So basically, we can also ask you, apart from displacement, this is velocity, right? Velocity at t, and that is velocity vector at t plus delta t. Do you agree?
Yeah.
So next, can I ask you, can we represent the display change? Can you represent the change in velocity? Do you want to try? Velocity is a vector, and in this diagram, here I just give you a hint. We can when we draw the vector, we can always translate the vector. Can you see? We can also do translation because this place need to be too crowded, right? So what can we do? We can copy as well. We can translate this vector here. You see? Okay. Or even we can also translate the second vector over here, because we are interested to find the difference. Do you agree?
Yeah.
So that's different vector. Okay. So if that's the case, how do we draw the change in the velocity? So that, remember, this is the velocity at time t, right? And this is the velocity. So that's this one is the velocity. Oh, I used to teach you. Yes, you are right. So that's it. So third question, another question, fourth. How do we denote to represent the acceleration? So how do we define acceleration vector? Sorry, we don't want to go that far. Okay, I let you know. That's enough. Okay, we will stop here, because when we draw acceleration, we have to consider Newton's law, right? No, we will not go that far. Perhaps let's just jump. You're all right. Okay, you are right. So basically, we can apply the vector to represent this real scenario. Perhaps next one is want to work out this exercise. So because after all, we're studying cross product. Okay. Cross product. I think this is a basic skill you need to learn. Product. Can we just do some exercise? For example, how about I cross product J? Have you studied this notation before? That's unity vector. Can you write down the result? We did some exercise before last week, right?
I think this is.
Oh no, we this I and J has a proper notation. So this IJK is actually
K.
Is K. Yeah, that's right. So in this particular example, we are dealing with the three direction in the space. So basically, we got yes, we got I have to write down here. So this is I, and this is a J. J. We just pay attention to this. A unit vector, and this is a k. That is a k. Okay, so they are all unit vector because their magnitude is always unit. So this is 1, 0, 1. This is 1. This is x and y. Yes, you can apply your right hand rule here. You just change that stated. How about I? Cross product k. So this is I. J. K. Negative J, right? So I use the right hand rule. You got I and the cross product, then you get negative J. That's right. That's right. Oh, can you put the, if you use your teacher's notation, can you put this underneath the vector? That is how to.
Oh, yeah.
Otherwise, it gives you something else. Okay, that's good. And now we just combine this exercise together. Okay, that is a dot product. And you combine this product. What is I dot product J? Oh, what is K? What is theta? K? Give me a K. You to K?
I don't know. I think there's another part of it. Maybe it's like K hat.
K hat? Well, I think you see, you're starting to mixing these two now. Can we just return to our page 1 today? So we have discussed the product. We have basically 2 different types of product, see? Now I just mix these 2. But it would appear you still stick with the vector product, right? I'm not asking, we're asking dot product. So by definition, what is the dot product of these 2? Cosine theta. Do we still have the K here at all?
Because I times J would be K anyway.
No,
right?
You see, yeah, be careful. You have to get used to it. And you cannot mix them up. No, you cannot. It's different. Okay, I just let you know. And A, and I use my notation. If I is A dot B has nothing to do with A. So that's a mistake. A student always, some student always makes mistakes. It's okay. So it's not true.
Yeah.
Why? Can you tell me why it is not true? Why it is wrong?
One scalar and one vector.
Yeah, you are not equal to. And besides, the dot product have nothing to do with this cross product. You see.
Yeah.
You have to perhaps write down the definition here. So when you're dealing with the dot product, you got the scalars. If I just write in ordinary letter, which means just the amplitude plus cosine constant. Okay, if I apply this formula, what can we do? Can we try again? If I use this formula here, how can we write this dot product on the right hand side? Yes, just ij cosine theta. Question is, what is theta?
The angle between I and J.
Yes, that is theta. What is theta? What is theta?
So 90 degrees.
Yes, 90 degree. Can you continue? Okay. Cosine 90 degree. Yeah. It's just I and J. So what is I and J? Further question.
1.
Yes, both are 1. Can you see? Both are 1. So therefore, it is 1, right? It is 1. So so in general, this apply to any. So how about whenever next time you say the J dot product K, how about this dot product of I and J? Sorry, I and K.
1.
Okay, it's 1. Okay. Now how about I? Oh, hang on. We have made a terrible mistake here. We are making a terrible mistake here. That is very fundamental. So this is not right. Can you say, be careful. The cosine 90 degree. What is value for cosine 90 degree?
0.
0. So the whole thing will be equal to 0, isn't it?
Yeah.
So that is actually this is criterion. So to see if the two vectors, so this implication, that's where we use this implication. So so if it's very useful. So if A perpendicular to B, right? So that is a general conclusion we can draw. Then what is the conclusion we can obtain? If that A equals to, so what is A dot B? Any vector, not I and J, any vector.
Equals 0.
That's right. So this is criteria we can use. Can you see? Eventually we'll use different criteria to judge, to make to solve the problem.
Yeah.
Okay. So that is a very useful criteria, although we make a mistake. So there should be 0, right? Should be 0. So that is why this is always the case, because that is that original design of this Cartesian coordinate. The direction of each vector, each x must be perpendicular to the rest of the axis. Okay. Yeah. Okay, let's just combine these two vectors together to some exercise. How about I cross product K and then cross product J. So this is combination. Are you sure? Can we do this step by step? Can you see? So can we just write this first? I cross product K first. Use the bracket. We use the. Can we find this first? Negative J. Okay, negative J. Then, therefore, we have the original product. So we have the negative J. How about negative J cross product J, the vector itself? Two vectors, actually, they are opposite.
Oh, that would be 0?
Why? Why 0? Good question.
Because if it's negative times positive, it's just going to cancel that out because negative.
No, it's not. No, it's not cancel. You have to use the proper algebra. Can you see? Can we just write down here? So that will give us negative J multiply J and sine theta. You cannot say cancel. So what is the theta in this case?
180.
Yeah, 180.
Yes. Oh, and that would be 0 because sine 180 is 0.
That's right. That is in this case, the direction of things 180 is pi, right?
Yeah.
So therefore, sine pi will equal to 0. Okay.
Yeah.
So that gives us another, we can call the theorem. It's just basically, so if in general, if the two vector parallel or anti-parallel, if A parallel to B, okay, or A parallel to just consider this situation is for you now. So what conclusion can we make? What is a product? What is the product of these two vectors?
It's equal to 0.
Yes. Can you see these are the implication? I think eventually you were going to learn, right? In your textbook. So that is how in mathematics we start some special case first, and eventually we generalize this property of vector into the general theorem. Okay.
Yeah.
All right. We still have some time. Can we go back to your textbook to see if we can pick up other content? All right. Now you can enlarge the second page we just saw here to see if you can solve these combination exercises. Okay, can you enlarge? Yeah, can you enlarge the second page so we can see? Can you? Okay, that's good. All right, all right. So can you see that we have done? Now we should be able to work out the vector product in components form. Can you see? That is how to. We have seen that. Can you see? Sometimes you got a positive IGK because they follow the right-hand row. So that will give you the positive K. Okay. Otherwise, another thing, if you exchange the order, if you change the order, you get something different. All right.
Yeah.
So another thing, this diagram, how do we interpret this diagram, the circle here?
If it's not the way the arrow is, then
which direction? Yeah, which direction you follow? IGK or if you can follow this circle either in clockwise or anti-clockwise, right? If you got clockwise, if you just count, right? You can just count. If you got clockwise, you should give always positive result.
Yeah.
Do you understand now? You can start from any position, and anything we should be okay. Let's go to the second page. They are trying to teach you how to use the matrix to solve the cross product issue, right? Yes. Yeah, that is something we can. Do you want to try? This time we just use our knowledge of the cross product of the unit vector to solve more complicated problem. Okay. Now this is a formula. Okay, this is a formula. Can we just I show you? Can we just go to whiteboard? I show you how to actually using this apply this knowledge to solve the problem before we use the general formula, right? For example, if you have the let's just go to whiteboard first. And so basically, if we just use this, it's just starting from the example. So if you have another example, okay, just consider cross product of two vectors, right? Two vectors. So this is just one of example. Okay, we just consider a vector equal to 2i minus 5j. Okay, this start from 2D first. All right. And the b vector is just 3i plus 4j. Can you work out the cross product of A cross product B? Do you want to try? Oh, you use a sum. How did you jump to sum? Can I show you how to do this problem? Can I?
Oh, do you have to sketch it first?
Or you have used a distribution law. Do you remember a distribution? You have 2i minus 5j. It's not simple. Cross product, can you see?
Mm-hmm.
And then that is 3i plus 4j. So then you have used your distribution algebra, can you see? So what you can do, you can multiply, cross product this first, second, third, fourth. You have 4 pairs to be dealt with. Okay, don't jump. That has nothing to do with the sum. Okay, this is a product. All right, can we try? Yes, it's a bit challenging for you. Oh, sorry. You got a 0. Where did you got a 0? Oh, you are right. The cross product of itself equal to 0. Is that right?
Yeah.
Oh, yeah. Yes. Can we just? But before that, can we write it as a dot? How to say cross? Where's my pen? My pen. Interesting. Oh, here. Can we just be careful? If you use your teacher's notation, then you have to consistently use the teacher's notation. Otherwise, you have to use this notation, all right? You have used first is I, can you see? Cross product I. And the number is, the first term is 2 multiply 3, right?
Yeah.
This is first term, okay? So what is the first term? Second term, second, third, the fourth. So what do you think? Cross product I cross product I equal to what?
0.
Yep, that is 6 multiply 0. You have to tell people this step. How did you derive this formula? All right. 0, okay. How about second term? You can write down on this side. Yeah. Or you have to also specify the cross product or not. Can you see? So you cannot put them together. You have to because they are dealing with vectors. Can you see?
Yeah.
You have to write this very carefully. It's cross product. Yes. So what is I multiply j?
K.
Yes, positive, right? Positive. Okay, you don't have this cross. You don't have write this cross anymore. Yeah, k. Yeah. Okay. That's right. Negative, right? Negative. Okay. Then, one moment. Did you change the sign or not yet? That is something you have to slow down when you first try this. In the step 3, we are dealing with J cross product I. Do you remember?
Oh, yeah.
Don't forget the order. That is at the beginning we have slowed down a little bit, right? That's right. It's also J cross product J. So if that's so, if you do want to write it this way, you have changed the order, isn't it? So that is something. No, keep that. You can keep that. Yeah, you can just put the negative here. if you understand that, right?
Mhm.
So in other words, can we write the general notation here? If you have the J correspond I, if you want to change it, the direction, if you want to change this order, that would become negative, right?
Yeah.
Of course, that is easy because this will give you K, isn't it? That is a K. That would be a negative K. Can you follow me?
Yeah.
So if you
Mhm.
change the order, you have to put the negative sign here. So that's why. Okay. That's it. Can you combine them together to, can we just clear this part? Can you write your result?
23K.
Yes. Same direction. Yeah, one is gives a positive number, another gives negative number, 20K. Yes. Well, that is how to do the cross product. So you still can, you see, when, to summarize today, so basically although we are dealing with new type of the mass quantity, the basic algebra law can still apply. Do you agree? For example,
Yeah.
we can find cofactor, we can distribute, expand, right? So that is how we're dealing with that. All right. Are you going to have the test next week?
There's a physics data test next week.
Just that test, no math test, right?
The maths test is in week 8.
Oh, not yet. Okay, not
Yeah.
yet. Okay. So we can discuss the physics this week, this Friday. Okay.
Mhm.
All right, I will save that, and we will continue next time.
All right. I'll see you Friday.
Okay.